A faint hiss fills the silent expanse of space, a ghostly whisper from the dawn of everything. This is the cosmic microwave background radiation, the ancient afterglow of the Big Bang itself. For years, we thought it was just uniform static, a blank screen of cosmic noise. We were wrong. This echo is a detailed treasure map, and scientists have begun to decode its secrets. By the end of this journey, you will understand 25 unbelievable discoveries hidden within this light, findings that challenge the very laws of physics and hint at realities beyond our own. What if the universe has a preferred direction, a strange alignment defying all expectations? Could a colossal cold spot be evidence of a collision with another universe? We are about to peel back the layers of cosmic history. What do you believe is the universe's greatest hidden secret? This cosmic whisper holds a secret so unsettling it was named the axis of evil. It suggests the universe might not be the same in every direction after all. The foundational rule of cosmology, the cosmological principle, states that the universe is homogeneous and isotropic. This simply means that on a large scale, it should look the same everywhere and in every direction, with no central point and no preferred axis. But the data from the cosmic microwave background tells a different story. When scientists mapped its subtle temperature variations, they found a strange alignment. Certain large-scale features, like the hot and cold spots, are not randomly scattered as expected. Instead, they appear to be coordinated, lining up in a specific plane that cuts across the sky. This alignment forms a mysterious axis, and it seems to correlate, bizarrely, with the plane of our own solar system and our motion through space. This is what we call the axis of evil. Data from the Planck satellite, our most detailed map of the ancient light, confirmed this eerie correlation. It is as if the universe's oldest echo is somehow aware of our local cosmic neighborhood. The name itself reflects how troubling this finding is to our standard models. Is this just a monumental statistical fluke, a one-in-a-million chance that we are seeing a pattern where none exists? Or is it a genuine crack in the foundation of cosmology, a ghostly imprint from a time before the Big Bang, a direction written into the fabric of space-time itself? This cosmic directional preference forces a profound question. Are we, despite everything we believe, in some way special? Or is this alignment a signpost to something even grander we have yet to understand? This cosmic axis is not the only ghost in the machine. Drifting in the ancient glow is a patch of cold so profound and so vast it seems to swallow the light of thousands of galaxies. This is the cold spot, a colossal anomaly in the cosmic background radiation that is significantly colder than its surroundings. For a long time, the most logical explanation seemed to be a supervoid, an immense bubble of space with far fewer galaxies and less matter than average. As light travels through such an underdense region, it loses energy, stretching to longer, colder wavelengths in a process known as the integrated Sachs-Wolfe effect. Think of it like climbing a hill and then rolling down the other side. Light entering the gravitational well of a void loses energy climbing out, leaving it cooler when it finally reaches us. But here is the mystery. Detailed surveys with powerful telescopes like the Atacama Cosmology Telescope have mapped the cold spot, and while they found a void, it is not nearly empty enough. The observed underdensity is simply too small to cause such a dramatic temperature drop. The numbers do not add up, leaving a chilling gap in our understanding. This discrepancy has fueled a far more exotic theory. Could the cold spot be a bruise, a cosmic scar from a collision with another universe in the vast multiverse? In this mind-bending scenario, the collision would have drained energy from that region of space, leaving behind a permanent cold imprint. The statistical unlikelihood of the cold spot occurring by chance makes it one of the strongest arguments for physics beyond the standard model. It is a tear in the fabric of reality that points to something stranger lurking in the background noise, something like the cosmic textures we are about to uncover. These cosmic defects are not mere blemishes, but fundamental kinks in the fabric of reality itself. As the newborn universe expanded and cooled in its first fleeting moments, a profound phase transition may have occurred. Think of it like water freezing into ice. When water freezes, the molecular structure changes, and sometimes defects like cracks or bubbles get trapped inside. In a similar way, as the universe's fundamental forces separated from one single superforce, the fabric of spacetime itself might not have smoothed out perfectly. It could have developed cosmic textures, tangled knots of energy frozen into existence. These textures are not made of matter, but are pure structure, topological defects in the fields that underpin everything. Finding one would be like discovering a fossil from the universe's first fraction of a second, a relic from an era of unimaginable energy. The hunt for these textures focuses on their unique signature imprinted on the cosmic microwave background. A cosmic texture is a gravitational anomaly, a region where the density of space is so warped it acts like a lens. As the ancient light from the Big Bang's afterglow passed by one of these knots, it would have been stretched and squeezed in a very specific way. This would leave a distinct circular pattern in the CMB, a bullseye of temperature variations with an intensely cold center surrounded by a hot ring. It is a fingerprint that cosmologists scan for in our detailed maps of the sky, a ghostly signature waiting to be found. The profound implication is that detecting a cosmic texture would be direct observational evidence for grand unified theories. These are the holy grails of physics, theories that attempt to describe how the electromagnetic, weak, and strong nuclear forces were once united as a single force. A texture is a prediction of such models, a tangible consequence of the universe's early symmetry breaking. This single discovery would forge an unbreakable link between the infinitesimally small world of quantum fields and the grandest scales of the cosmos, a bridge built from a defect in spacetime. And just as we search for these massive structures, we must also look for the smallest possible ripples, the primordial whispers that grew into everything we see. The hunt for these cosmic defects leads us even further back to the very first instance of time. To understand the universe's largest structures, we must listen for its faintest whispers, ripples born from the most violent expansion imaginable. This is the story of cosmic inflation, a theory proposing that a fraction of a second after the Big Bang, the universe underwent an exponential growth spurt, inflating from smaller than an atom to a vast cosmic scale in an eye blink. This event would have been so cataclysmic that it should have shaken the very fabric of spacetime, generating primordial gravitational waves. These are not waves in water or air, but literal ripples in the dimension of space and time itself. They are the oldest possible vibrations in the cosmos, a relic from its first moment of existence, and we hunt for their ghostly signature etched into the cosmic microwave background. The key lies in the polarization of this ancient light. As the initial gravitational waves from inflation rippled through the hot, dense plasma of the early universe, they would have imparted a very specific, swirling pattern onto the light, a fingerprint known as B-mode polarization. Finding this distinct swirl in the CMB is the ultimate goal, as it would be incontrovertible proof that inflation truly happened. The search for this signal has been one of the most dramatic pursuits in modern cosmology. Experiments like BICEP, located at the South Pole to take advantage of the incredibly dry, clear air, made headlines around the world when they announced a potential detection. The excitement was palpable, a potential Nobel Prize-winning discovery, but the story was not so simple. The Keck Array telescopes, along with data from the Planck satellite, revealed a formidable challenge. The delicate B-mode pattern they thought was from primordial waves was almost entirely masked by a foreground contaminant, cosmic dust within our own Milky Way galaxy. This interstellar dust, when illuminated by starlight, can create a polarization signal that mimics the very pattern scientists were desperately seeking. It was a sobering lesson in cosmic humility. The quest continues with ever more sensitive instruments, painstakingly mapping the sky to separate the faint whisper of inflation from the loud foreground noise of galactic dust. Success would do more than just confirm a theory. Detecting these primordial ripples would tell us the energy scale of the universe's birth. It would reveal the sheer, unimaginable force that drove inflation, opening a direct window into the laws of physics at energies 1 trillion times greater than any particle collider on Earth could ever reach. This single discovery would set the stage for understanding the universe's initial conditions, the very reason our cosmos looks the way it does. And if we can find the waves that shaped the cosmos, what about the sound that once filled it? But the echoes of that ancient sound hold more than just whispers of creation. They also contain a number that refuses to agree with itself, a discrepancy so stubborn it has thrown modern cosmology into a state of profound crisis. We call this the Hubble Tension. At its heart is a simple question with a deeply complicated answer. How fast is the universe expanding right now? This expansion rate is quantified as the Hubble constant, and for decades we have had two reliable ways to measure it. The first method looks at our local cosmic neighborhood. Astronomers observe nearby galaxies, measuring their distances and how quickly they are moving away from us. This gives us a direct present-day measurement of the Hubble constant. It is like using a radar gun on the cosmos. The second method uses the cosmic microwave background as a time capsule. The detailed pattern of hot and cold spots in the CMB, meticulously mapped by the Planck satellite, is a frozen record of the universe at age 380,000 years. Scientists feed this pattern into our standard model of cosmology, which projects the evolution of the universe forward in time to predict what the expansion rate should be today. This is a backward-looking approach, extrapolating from the infant universe to the present. The problem is stark. These two methods, one local and direct, the other ancient and theoretical, give stubbornly different answers. The universe today appears to be expanding faster than our best model, based on the pristine early universe, says it should be. The gap is not a small observational error. It is a significant and persistent tension that has survived years of reanalysis and improved measurements. So what does this mean? Could there be a previously unknown form of dark energy that briefly surged in the recent cosmic past, giving expansion an extra kick? Perhaps the universe contains additional, exotic relativistic particles that we have not yet accounted for, subtly changing the rate at which structures formed. Or, most unsettling of all, could this be a sign of a fundamental flaw in our standard cosmological model, the lambda cold dark matter model, which has been the bedrock of our understanding for decades? This is not just a minor accounting error. It is a direct challenge to our most successful description of reality, forcing us to question if we truly understand the dark components that make up 95% of the cosmos. This single number, the Hubble constant, has become a battleground of ideas, a mystery that pushes us to the very edge of known physics. This stubborn disagreement over the universe's expansion is not the only crack in our cosmic foundation. Even our understanding of the universe's very first few minutes is facing a puzzling anomaly, one locked within the creation of the simplest atoms. The Big Bang theory performs a spectacular feat of prediction. By knowing the conditions of the early universe, physicists can calculate with stunning accuracy how much of the lightest elements should have been forged in the nuclear furnaces of the first 3 minutes. The predicted amounts of hydrogen and helium match what we observe throughout the cosmos almost perfectly. It is a triumph of modern cosmology, but there is a single, glaring exception. Lithium. The theory overpredicts the amount of lithium-7, the most common isotope of this element, by a factor of 3. We see only about a third of the lithium that our models insist should be out there. This is the cosmological lithium problem. The mystery has only deepened with our precise maps of the cosmic microwave background. The CMB allows us to measure the baryon density, which is the amount of ordinary matter in the universe, with incredible precision. This measurement locks in the predictions for Big Bang nucleosynthesis, removing it as a variable. The result is that the lithium discrepancy is not a loose end that can be explained away by adjusting other parameters. It is a real and severe problem. So where did the lithium go, or was it never made in the expected quantities to begin with? Scientists have proposed fascinating solutions that stretch the boundaries of known physics. Perhaps our understanding of the nuclear reactions themselves is incomplete. Maybe unknown particles were present in that primordial soup, subtly altering the reaction rates that built lithium nuclei. Another compelling idea involves hypothetical dark matter particles. Certain types of these unseen particles could have decayed in the early universe, releasing energy that would have broken apart the fragile lithium nuclei as they were forming. This would essentially erase the lithium signature we now find missing. The lithium problem is a small but persistent crack in the otherwise solid edifice of Big Bang nucleosynthesis. It serves as a humble reminder that the universe's first few minutes, a period we thought we understood so well, still hold profound secrets. And just as the creation of matter itself holds anomalies, so too does the motion of the galaxies we see today. This mysterious motion of galaxies echoes a far grander and more unsettling cosmic drift. While the universe expands, carrying galaxies apart on the river of spacetime, something else is happening. Entire clusters of galaxies, thousands of them, appear to be streaming in a specific, coherent direction. They are moving as if pulled by a cosmic current, at speeds of over 1,000,000 miles per hour. This is not the gentle drift of expansion, but a determined flow, and it has been named the dark flow. Detecting this subtle motion required a brilliant piece of cosmic detective work, using the cosmic microwave background as a fixed backdrop. Scientists employ what is known as the kinetic Sunyaev-Zeldovich Effect. Here is how it works. As the hot gas within a galaxy cluster moves through space, the photons of the CMB radiation scatter off the electrons in that gas. If the cluster is stationary relative to the CMB, the scattering is symmetric. But if the cluster is moving, the photons get a slight push, a Doppler shift. This imprints a very subtle temperature distortion on the CMB in the direction of that cluster's motion, a tiny hot or cold spot that acts like a cosmic speed camera, recording the cluster's velocity. When astronomers compiled the data from hundreds of clusters, they found they were not moving randomly. A significant number were streaming toward the same patch of sky, a direction that seems to point toward the constellations Centaurus and Vela. The most compelling and controversial explanation for this dark flow is a gravitational pull from something so immense it lies beyond our ability to see it. We are talking about matter that resides outside our observable universe. The observable universe is the spherical region from which light has had time to reach us since the Big Bang, a bubble about 93 billion light-years across. But the entire universe is almost certainly much, much larger, possibly infinite. If there is a vast, massive structure just beyond our cosmic horizon, a supercluster of unimaginable scale, its gravitational influence could be reaching across the void and tugging on everything in our neighborhood. This is not a force traveling faster than light, but rather the persistent pull of a gravity well that has always been there, influencing the motion of galaxies since the beginning. The evidence remains hotly debated, with some analyses supporting the flow and others finding no statistical significance. But if it is real, the implications are staggering. It would mean we can indirectly detect the structure of the unobservable universe. Our entire local cosmos, everything we can see, would be adrift in a much grander ocean, pulled by shores we can never glimpse. This notion flows directly into the most profound ideas of a multiverse, suggesting that what we call the universe is just one island in an infinite archipelago, and the tides between them are strong enough to move galaxies. This cosmic drift hints at structures beyond our vision, but the whispers of creation hold an even more subtle secret, one written in the statistics of the ancient light itself. The patterns we see in the cosmic microwave background are not just a random collection of hot and cold spots. They follow a specific mathematical order, and that order is the key to unlocking the universe's first split second. For the most part, the fluctuations in the CMB are what statisticians call Gaussian. This means their distribution follows the familiar bell curve, where extreme deviations, like a spot that is intensely hot or profoundly cold, are very rare, while most spots cluster around the average temperature. It is a pattern of random chance, the kind you would expect from simple quantum jitters stretched across the cosmos during inflation. But what if the pattern is not perfectly random? What if there are subtle correlations, hidden connections between these spots that defy the simple bell curve? This deviation is what cosmologists call non-Gaussianity. Finding it would be like discovering a fingerprint in the chaos, a signature of specific physical processes at work during the universe's violent birth. The hunt for non-Gaussianity is a hunt for the detailed physics of inflation. Different models of this rapid expansion predict different types of interactions between the quantum fields that drove it. Think of it like the surface of a pond. If you simply heat the water, the surface will jiggle with random Gaussian ripples. But if you stir the water with a specific, complex motion, the ripples will show correlations and patterns that are not random at all. They will be non-Gaussian. In the same way, if the inflationary field had complex self-interactions, or if there were multiple fields influencing each other, those interactions would have left a specific, non-Gaussian pattern imprinted on the CMB. Detecting this signal is incredibly difficult because it is so faint, buried deep within the noise, but the payoff would be monumental. It would effectively allow us to see the physics of the universe's first moments, distinguishing between the many competing theories of inflation. It would tell us if inflation was driven by a single, simple field or a more complex symphony of forces. This single statistical anomaly would provide a direct link to the fundamental laws that govern creation itself, offering a glimpse into the quantum realm operating at the highest energies conceivable. And by understanding these initial conditions, we take a crucial step toward answering one of cosmology's oldest questions, the very shape and geometry of the cosmos we call home. The geometry of our universe is not curved but perfectly flat. This is not a flatness like a sheet of paper, but a flatness of space-time itself, a profound discovery etched into the pattern of the cosmic microwave background. The hot and cold spots in that ancient light act as a fixed cosmic ruler. Scientists know the theoretical maximum size these spots could have been when the universe was just 380,000 years old. A scale set by the distance sound waves could travel in that hot, dense plasma. By measuring the actual angular size of these spots on the sky today, they can perform a simple geometric test. In a positively curved, closed universe, like the surface of a sphere, parallel light rays would converge, making these spots appear larger than they should. In a negatively curved, open universe, like a saddle, light rays would diverge, making the spots appear smaller. The data from the CMB shows the spots are exactly the size predicted for a flat universe, where parallel light rays travel forever on a straight path. This geometric flatness has staggering implications. It tells us the universe exists in a state of precise, critical balance. The total density of all the matter and energy in the cosmos, including the dark, mysterious components we cannot see, adds up to exactly the amount needed to halt any large-scale curvature. This perfect balance strongly supports the theory of cosmic inflation, as that violent initial expansion would have stretched the fabric of spacetime so thin that any primordial curvature was smoothed into flatness, just as blowing up a balloon immensely makes its surface appear locally flat. For the ultimate fate of the cosmos, a flat universe suggests a slow and lonely end. It will continue expanding forever, but at a rate that gradually slows, with galaxies fading from view over trillions of years in a cosmic heat death. This flat geometry also acts as a strict constraint on the nature of dark energy and dark matter. Any viable model for these enigmatic forces must reproduce the universe's exact flatness we observe. It is a finding that seems to finalize the large-scale structure of reality, a fundamental parameter now seemingly locked in place by the echo of the Big Bang itself. Even the geometry of spacetime itself might be knotted with defects of impossible scale. Laced through the cosmos could be cosmic strings, filaments of pure energy thinner than a proton yet stretching across the entire observable universe. These are not strings in the everyday sense, but one-dimensional tiers in the fabric of reality, predicted by many advanced particle theories. They are relics of a phase transition in the universe's first moments, when the fundamental forces were finding their separate identities. As the cosmos cooled, these immense, stable defects could have been frozen into existence like cracks forming in ice. Detecting one would be like finding a fossil from the first split second of time, a thread leading directly back to the laws that govern everything. The hunt for these cosmic strings focuses on their unique and dramatic signature in the cosmic microwave background, an effect named for the scientists who predicted it. As a cosmic string moves through space at nearly the speed of light, its immense density warps spacetime around it, creating a gravitational lens. This lens is so sharp and thin that it acts like a razor's edge. When the uniform light of the CMB passes by on either side of this edge, one side's light gets blue-shifted, appearing slightly hotter, while the other side gets red-shifted, appearing colder. The result is a sudden, step-like discontinuity in the temperature map of the sky, a clean line where the temperature jumps from one value to another. This Kaiser-Stebbins effect is a ghostly scar, a linear tear in the ancient afterglow that nothing else can easily explain. Finding such a line would be a monumental discovery, a direct validation of concepts from string theory and supersymmetry. These theories attempt to unify all the forces of nature, including gravity, and they often predict the existence of such exotic objects. A cosmic string would be tangible evidence that these abstract ideas are grounded in physical reality. The properties of the string, its tension and how it interacts, would even tell us about the number of fundamental families of particles in the universe, providing a crucial link between the cosmic scale and the quantum world. While no confirmed cosmic string has yet been found, The search continues in ever more detailed maps of the CMB, scanning for that perfect, impossible line etched by a thread from the beginning of time. These ghostly strings are not the only relics haunting the cosmic background. The same ancient light that reveals the geometry of space-time also serves as a cosmic neutrino counter, measuring the invisible sea of ghostly particles that flood the entire universe. These are relic neutrinos, trillions of which pass through your body every second without a trace, left over from the first second after the Big Bang. When the cosmos was a searing hot plasma, neutrinos were trapped, constantly interacting with electrons and photons. But when the universe was just 1 second old, it cooled enough for these particles to decouple, flying freely through space and barely interacting with anything ever again. This cosmic neutrino background is the second oldest relic we can study, after the CMB itself, and its imprint is subtly written into the power spectrum of the microwave background. The presence of these neutrinos influenced how the primordial plasma sloshed back and forth in those first moments. Their slight gravity and their tendency to stream freely out of dense regions acted as a dampening effect on the oscillations of the hot plasma. This left a specific, measurable suppression in the amplitude of certain temperature fluctuations in the CMB. By analyzing this detailed pattern, cosmologists can effectively count the number of light neutrino species that were present in the early universe. The result is a profound confirmation of the standard model of particle physics, which predicts 3 families of neutrinos. Yet here too, the cosmos whispers of a possible anomaly. Some detailed analyses of the CMB data have persistently suggested a slight excess, a hint that the effective number of neutrino species might be a little more than 3. This has ignited speculation about the existence of a 4th, sterile neutrino. Unlike the 3 known types that interact via the weak nuclear force, a sterile neutrino would interact only through gravity, making it even more elusive and impossible to detect with conventional particle detectors. This cosmological measurement provides a unique, large-scale complement to the smash and detect experiments at particle accelerators like the Large Hadron Collider. While those machines probe the smallest scales, the CMB offers a census of the entire universe's most elusive inhabitants, taken over the grandest possible laboratory. A confirmed detection of a sterile neutrino would shatter the standard model, forcing a rewrite of the rules for both particle physics and cosmology, revealing a hidden actor that helped shape the evolution of the cosmos from its very first breath. That invisible sea of ghostly neutrinos is not the only ancient signal imprinted on the cosmic background. The very same light holds the story of how the universe woke up from its dark ages and saw its first dawn. For hundreds of millions of years after the Big Bang, the cosmos was a vast dark fog. The hot plasma had cooled into a sea of neutral hydrogen gas, blocking the passage of any visible light. The universe was a silent, featureless gloom. Then something switched on. The first stars and galaxies ignited, and their fierce ultraviolet radiation began to tear apart those neutral hydrogen atoms, stripping away their electrons in a process called reionization. This was the final major transition of the cosmos, the moment it became the transparent, ionized universe we see today, and we can read the history of this epic dawn in the CMB's polarization. As the first intense light flooded the cosmos, it did more than just ionize gas, it also polarized the ancient microwave background radiation. The free electrons scattering this light imprinted a specific curling pattern known as E-mode polarization. This is not the swirling B-mode pattern from primordial gravitational waves, but a more direct curl-free signature that acts as a fossil record of when and how quickly reionization occurred. The data from the Planck satellite provided a stunningly precise measurement of this epoch, It revealed that the process of reionization began around 400 million years after the Big Bang, which is later than many early models had predicted. This tells a crucial story about those first luminous objects. They were not instantly abundant. It took time for the first stars to form, gather into galaxies, and finally produce enough collective radiation to burn through the cosmic fog. This delay suggests the very first stars and galaxies were incredibly efficient and powerful ionizers, their brilliant, short-lived lives flooding the darkness and clearing the way for everything that would follow. The E-mode polarization is therefore more than just a pattern. It is a timestamp for the dawn of structure, a direct measurement of when the lights first came on across the cosmos. This pivotal chapter illuminates the birth of galactic structures, setting the stage for the universe we now observe, a universe that may be filled with far more matter than we can possibly see. Magnetic fields weave through the cosmos, a hidden force within galaxies and the vast spaces between them. For a long time, astronomers assumed these fields were generated later in the universe's life, forged by the turbulent motions of gas within galaxies and clusters. But a more profound possibility is now emerging from the cosmic static. What if these fields are primordial, born in the universe's first chaotic moments, and imprinted directly onto the fabric of spacetime? The hunt for their ghostly signature leads us back once again to the ancient light of the cosmic microwave background. A primordial magnetic field, a relic from the first second after the Big Bang, would not have been a passive spectator. As the CMB photons began their journey across the universe, these fields would have gently twisted their path. This interaction would leave two distinct fingerprints. First, it would create specific, subtle distortions in the temperature map of the sky, a slight stretching and squeezing of the hot and cold spots. Second, and more tellingly, it would generate a unique pattern of polarization, a specific swirl in the light's orientation that is different from the patterns created by inflation or reionization. Finding this specific swirl would be like discovering the cosmic seeds for the magnetic giants we see today. The implications are staggering. If these fields are primordial, they would have been present at the very dawn of structure formation. Their subtle pressure could have acted as a scaffold, a guiding framework around which the first wisps of matter began to coalesce. They would have provided the initial push, helping to pull together the gas that would eventually collapse into the first stars and galaxies. This would solve a major cosmic mystery, revealing not just how magnetic fields were born, but also how they helped to build the universe we inhabit. Current data from observatories like the Planck satellite have not yet found a definitive signal, but they have set strict upper limits, telling us just how faint these primordial fields must be if they exist at all. The quest now falls to a new generation of experiments, like the Simons Observatory and CMB-S4, with unprecedented sensitivity. They will scan the ancient light for that faint, swirling polarization, a pattern that would confirm a force at work since the very beginning, a fundamental energy that helped to write the blueprints for all cosmic structure. This ancient light does not travel to us on a straight path. The cosmic microwave background radiation on its 14 billion-year journey has been subtly warped and distorted. The very fabric of space it travels through is not empty, but is curved by the gravitational pull of all the matter in its path, especially the vast, unseen reservoirs of dark matter. This phenomenon is known as gravitational lensing, and it has turned the CMB into the ultimate backlight for mapping the invisible skeleton of the cosmos. To see this effect, scientists do not look for bent images as they would with a distant galaxy. Instead, they perform a kind of cosmic statistics on the CMB map itself. The primordial hot and cold spots, which should be statistically isotropic and random, show tiny, coherent correlations. Their shapes appear ever so slightly stretched and sheared, as if viewed through a vast, lumpy lens. This subtle distortion is the telltale fingerprint of dark matter bending the light's path. By applying incredibly sophisticated algorithms to the data from the Planck satellite, cosmologists can reverse engineer this distortion. They can essentially calculate what distribution of mass must have been between us and the CMB to create the specific pattern of stretching they observe. The result is a rough, all-sky map of the total mass in the universe, a web of dark matter that traces the cosmic large-scale structure. This map is revolutionary because it is a direct gravitational probe of dark matter, independent of any assumptions about galaxies or their light. It confirms that dark matter clumps together exactly as our models predict, forming a cosmic scaffold upon which galaxies are built. But the power of this lensing map goes even further. By precisely measuring how clumpy this dark matter distribution is, scientists can weigh the universe's lightest known particles. Relic neutrinos streaming freely through the cosmos have a subtle but measurable effect. Their tendency to smooth out small-scale clumps acts as a damper on the gravitational lensing signal. By analyzing this damping, researchers can place the tightest constraints yet on the sum of neutrino masses, a measurement that terrestrial experiments can only dream of. Furthermore, the way this lensing effect evolves over cosmic time provides an independent check on the nature of dark energy. Dark energy's repulsive force works against gravity, slowing the growth of these massive structures over the eons. By comparing the lensing map derived from the ancient CMB with maps made from younger sources of light, like distant galaxies, we can see this slowdown in action, testing our most fundamental ideas about the fate of the universe. This same ancient light offers a geometric test for the most mysterious force in the cosmos. We call it the Alcock-Paczynski Effect, a subtle but powerful tool for probing the true nature of dark energy. To understand it, picture a distant spherical cluster of galaxies. We know its true physical diameter from our models of cosmic structure. Now we measure how it appears on the sky. We see its angular size, how wide it looks from our vantage point. We also measure its depth along our line of sight, but not with a ruler. We use the redshift of its light, which tells us how much the universe has stretched since that light was emitted. These two measurements, the angular size and the redshift depth, act as cosmic yardsticks, but they depend critically on the geometry of the universe between us and the object. In a universe dominated by a simple cosmological constant, the yardsticks will show a specific, predictable relationship. But if dark energy is something more complex, a dynamic field that changes over time, it warps this relationship. The sphere would appear distorted, either squashed or stretched, depending on the properties of the dark energy. The cosmic microwave background provides the perfect, fixed reference object for this test. Its sound wave spots have a known physical scale, acting as a standard ruler etched across the entire sky. By comparing this ancient ruler with the apparent sizes of much younger structures, like the vast baryon acoustic oscillations imprinted in the distribution of galaxies, we can see if the cosmic geometry has evolved as expected. This cross-check is incredibly powerful. It measures the equation of state of dark energy, a single number that tells us if this force is constant or evolving. Is it the steady vacuum energy of a cosmological constant, or is it a phantom energy that grows stronger, or perhaps a quintessence field that slowly fades? The current data, combining CMB maps with enormous galaxy surveys, points strongly toward the simple cosmological constant. Yet, the measurements are not yet so precise that they rule out more exotic possibilities. Each new, more detailed survey sharpens this test, tightening the constraints on what dark energy can be. It is a quiet, geometric whisper that may finally reveal whether the force tearing our cosmos apart is eternal and steady, or a temporary visitor in the long story of the universe. These cosmic defects form a menagerie of impossible structures, from one-dimensional strings to two-dimensional walls and even point-like singularities. Domain walls are envisioned as immense, sheet-like boundaries, surfaces that separate regions of space where fundamental fields have settled into different states. Think of the early universe as a vast tray of water freezing into ice. As it solidifies, different ice crystals form, and where they meet, a distinct boundary, a crack or a plane, is created. A cosmic domain wall is like that, but on a universal scale, a two-dimensional surface of concentrated energy where the vacuum of space itself changes character. If such a wall were to slice through our line of sight to the cosmic microwave background, its gravitational influence would be immense. It would create a sharp, step-like discontinuity in the temperature of the ancient light, a clean dividing line across the sky where one side is distinctly hotter and the other colder. It would be a scar of impossible geometry, a rip in the cosmic canvas. Then there are magnetic monopoles, perhaps the most elusive of all. In our everyday world, magnets always have two poles, a north and a south. You can break a magnet in half, but you only get two smaller magnets, each with its own north and south pole. A magnetic monopole, however, is a hypothetical particle that is just a north pole or just a south pole, a singular magnetic charge. Many grand unified theories insist that these monstrous particles must have been created in staggering abundance during the universe's first moments. Finding just one would be a revolution, while a single monopole would be too small to directly affect the CMB. A dense network of them in the early universe, or their collective gravitational influence, could have left a statistical imprint on the pattern of hot and cold spots we observe today. The profound significance of discovering any of these defects cannot be overstated. They are not just cosmic curiosities, they are direct, tangible evidence of the phase transitions that shape the cosmos, moments when the fundamental forces of nature, like electromagnetism and the weak and strong nuclear forces, broke their symmetry and went their separate ways. Each type of defect, strings, walls, textures, and monopoles, is a prediction of a different version of this cosmic story. Finding one would tell us precisely which path the universe took, which set of physical laws were written into reality at the beginning. It would offer concrete evidence for theories that operate in realms of higher dimensions, realms we cannot perceive, suggesting that the fabric of our reality is just a shadow of a far richer, more complex structure. The search for these ghostly imprints is a hunt for the very architecture of creation, a blueprint hidden in the noise. The universe displays a strange and fundamental lopsidedness. Across the vast map of the cosmic microwave background, one half of the sky is subtly but undeniably different from the other. This is the hemispherical power asymmetry, a discovery that reveals one celestial hemisphere has slightly stronger, more powerful temperature fluctuations than its opposite. The hot and cold spots are not distributed with the same statistical strength everywhere. It is as if the primordial universe had a preferred side, a more active half, challenging one of cosmology's most cherished principles, statistical isotropy. This principle asserts that the universe, on the largest scales, should look the same in every direction, with no special regions or preferred axes. The asymmetry we observe is a direct violation of this rule, a cosmic flaw in the fabric of symmetry. So what could cause such a fundamental imbalance? One compelling idea points back to the inflationary epoch. Perhaps the field that drove the universe's explosive early expansion was not perfectly uniform. It might have contained a gradient, a slight slope in its energy, meaning one region of space inflated with marginally different properties than another. This would have imprinted a directional bias onto the entire cosmos, a fossilized lopsidedness from the first moment of time. Another, even more profound explanation involves gravitational waves on a scale so vast it is difficult to comprehend. These are not the tiny ripples detected by observatories on Earth, but colossal undulations in spacetime from the inflationary period. A single, dominant wave of this nature, frozen at the moment it stretched beyond the cosmic horizon, could have created a persistent anisotropy, a permanent warp that makes one half of the sky appear statistically different from the other. This leads to the most mind-bending possibility of all, that our universe is not a perfectly isolated bubble, but part of an anisotropic multiverse. In this scenario, the asymmetry is a ghostly influence from a neighboring cosmos, a universe with entirely different physical constants. Its gravitational pull, or the residual energy from a long-ago collision, could be tugging at the fabric of our own reality, leaving one hemisphere of our sky forever marked by an external presence. This lopsidedness is more than a curiosity, it is a fundamental clue. It suggests that the process of creation was not perfectly smooth and symmetric, but was textured with flaws and gradients that have shaped everything we see. This cosmic imperfection forces us to ask if our entire observable universe is just a local patch within a far grander and more varied structure, a single lopsided room in an infinite, asymmetrical mansion. Even the faintest static in the cosmic background holds a story. What we once dismissed as mere contamination in the pristine map of the Big Bang's echo has revealed itself to be a treasure trove. Scattered across the ancient glow are countless pinpricks of light, individual points that are not part of the background at all. These are foreground objects, distant quasars, and incredibly luminous galaxies, and their emission was once considered noise to be cleaned away. But with missions like Planck, this noise has been transformed into one of the most valuable catalogues in modern astronomy. These point source catalogues are a census of the distant universe, a directory of celestial phenomena compiled from the static. The process is a masterclass in cosmic filtering. By observing the sky at multiple frequencies, scientists can isolate the unique spectral signature of these distant objects from the uniform haze of the CMB. The result is a collection of hundreds of thousands of confirmed sources, a mass-limited sample that is not biased by the quirks of traditional observation. This means we are seeing some of the most intrinsically luminous and massive objects across the cosmos, many of them so far away we are seeing them as they were billions of years ago. These catalogues are crucial for tracing the evolution of cosmic structure. By comparing the numbers and properties of these dusty, star-forming galaxies and brilliant quasars at different distances, we can watch how they have changed over cosmic time. How did the first monstrous galaxies assemble themselves? When did star formation peak across the universe? The answers are hidden within this directory, a byproduct of mapping the oldest light. This is the ultimate astronomical repurposing, turning the universe's background noise into a field guide for its most spectacular inhabitants. The universe's ancient light does more than just reveal its own history. It acts as a brilliant backlight for everything in its path. A ghostly shadow falls across the cosmic microwave background, a subtle imprint left by the largest structures in the universe. This is the Sunyaev-Zeldovich Effect, a phenomenon that turns the CMB into a cosmic scanner for galaxy clusters. Here is how it works. The space between galaxies in a massive cluster is not empty. It is filled with a searingly hot, thin gas. As the photons of the CMB travel for billions of years to reach us, some of them pass directly through one of these enormous clouds of plasma. The electrons in this superheated gas are moving incredibly fast, and when a cool, ancient CMB photon collides with one of these energetic electrons, it gets a kick, a boost in energy. This interaction, known as inverse Compton scattering, leaves a specific fingerprint. At the low frequency where the CMB is brightest, the cluster appears as a shadow, a slight dip in temperature against the glowing background. But at higher frequencies, that same cluster appears as a bright spot. This unique spectral signature is unmistakable, a celestial barcode that identifies the presence of a massive galaxy cluster. The power of this technique is its independence from distance. Unlike optical telescopes that struggle to see the faintest, most distant galaxies, the SZ effect works just as well for a cluster 10 billion light-years away as it does for one nearby. The shadow it casts depends only on the density and temperature of the hot gas in the cluster, not on how far away the cluster is. This has allowed astronomers to compile vast catalogues of SZ-selected clusters, thousands of them, building a census of the most massive gravitationally bound objects across cosmic time. These catalogues are not just a list, they are a powerful cosmological tool. By counting how many clusters of a given mass exist at different epochs in the universe, scientists can measure the growth of cosmic structure. Gravity pulls matter together over time, forming more and more massive clusters. The rate of this growth is exquisitely sensitive to the fundamental ingredients of the cosmos, especially the nature of dark energy and the mass of neutrinos. Those ghostly neutrinos streaming freely at nearly the speed of light have a smoothing effect. Because they are so light and fast, they do not clump together in the way dark matter does. This suppresses the formation of the very smallest clusters. By comparing the observed number of clusters to theoretical predictions, cosmologists can place the tightest constraints on the sum of all neutrino masses. It is a remarkable chain of discovery, using the faded afterglow of the Big Bang to illuminate vast cities of galaxies, which in turn reveal the properties of the universe's most elusive particles. Even the most uniform whisper of the cosmos reveals a fundamental direction. The cosmic microwave background is not perfectly even. It carries a distinct and dominant pattern known as the dipole. One half of the sky is measured to be slightly warmer, while the exact opposite direction is subtly colder. This is not a random fluctuation or a hidden mystery, but a brilliant confirmation of our own motion through the universe. We are moving at a staggering 600,000 miles per hour toward the constellation Leo, and the CMB dipole is our cosmic speedometer. The effect is a simple yet profound Doppler shift. Just as the pitch of a siren rises as an ambulance races toward you and falls as it moves away, the ancient light of the Big Bang is blue-shifted and thus slightly warmed in the direction we are heading. In the direction we are fleeing, the light is redshifted and cooled. This measurement defines the ultimate rest frame for the cosmos, the coordinate system where the afterglow of creation is truly isotropic. From this, we can calculate our precise velocity relative to this primordial backdrop, seeing not just the Earth's orbit around the Sun, or the Sun's path around the galaxy, but the entire Milky Way's grand trajectory through the cosmic ocean. Yet, a subtle question lingers beneath this clear explanation. Is this entire dipole truly just from our local motion, or could a tiny fraction of it be a genuine cosmological anisotropy, a whisper of a lopsided universe imprinted at the beginning? Most of the signal is indeed our own motion, but some cosmologists speculate that a small residual might be part of the universe's fundamental character, a connection to the larger hemispherical asymmetries and the mysterious dark flow. This single, clear measurement grounds us in a profound way. It tells us our exact address and velocity within the vast expanse, a celestial anchor point in the flowing river of spacetime. This ancient echo has become the ultimate testing ground for the very laws of gravity. The cosmic microwave background's detailed pattern is a record of how matter clumped together over billions of years, a process governed by the relentless pull of gravity. Any alternative theory of gravity, any proposal to modify or replace Einstein's general relativity, must be able to reproduce this exact pattern to be taken seriously. The universe has provided us with the answer sheet, and any new theory must match it perfectly. Consider theories like modified Newtonian dynamics or MUND, which propose that we do not need dark matter if we adjust how gravity behaves at very low accelerations. While MUND can explain some properties of individual galaxies, it faces a monumental challenge in the cosmic microwave background. The intricate dance of hot and cold spots, the specific peaks and troughs in its power spectrum, were sculpted by the gravitational influence of dark matter pulling on the primordial plasma. Without a significant amount of this unseen matter, the theoretical predictions for the CMB look nothing like the map we actually observe. The same is true for more complex theories like F of R gravity, which modify how space-time curves in response to mass and energy. These models must not only explain the accelerated expansion we attribute to dark energy, but they must also precisely replicate the entire history of cosmic structure formation encoded in the CMB. So far, every test has come to the same stark conclusion. The standard model of cosmology, which pairs Einstein's general relativity with dark matter and dark energy, fits the CMB data with breathtaking accuracy. This does not completely rule out every alternative, but it forces them into a very narrow corner. To match the data, most modified gravity theories end up requiring some form of dark matter or dark energy anyway, making them more complicated without providing a clearer answer. The cosmic microwave background has thus become a powerful arbiter, a cosmic referee in the fundamental quest to understand the true nature of gravity. It tells us that on the largest scales across the entire observable universe, Einstein's theory, paired with these mysterious dark components, remains the most precise description of reality we have. Even the faintest whisper of the CMB can be amplified by the structures it passes, revealing a direct tug of war between gravity and dark energy. When a photon from the cosmic microwave background travels across the cosmos, its journey is not a simple flight through empty space. It climbs in and out of the gravitational wells created by massive galaxy clusters and the vast cosmic web of dark matter. Normally, as it climbs out of a well, it should lose exactly as much energy as it gained falling in, leaving its final temperature unchanged. But our universe is not static, it is expanding at an accelerating rate. This acceleration, driven by dark energy, causes those immense gravitational wells to become shallower over time. The photon falling into a deep well gains a certain amount of energy, but when it climbs out, the well has become slightly shallower due to the universe's expansion, so it does not have to expend as much energy to escape. It emerges with a net gain, appearing slightly hotter or blue-shifted. Conversely, a photon traveling through a large, underdense void, a cosmic hill, will find that hill has stretched and become wider. It loses more energy crossing this expanding region than it gained entering it, leaving it slightly colder or redshifted. This subtle energy transfer is the integrated Sachs-Wolfe effect. The signal is incredibly faint, far too weak to see in a single spot on the CMB map. To detect it, scientists perform a cosmic correlation. They take a detailed map of the universe's large-scale structure, showing the locations of millions of galaxies and the voids between them, and they overlay it with the CMB temperature map. Where they find a statistical correlation, where hot spots in the CMB consistently align with massive clusters and cold spots align with vast voids, they have found the fingerprint of the ISW effect. This is not just another hint, it is direct dynamical evidence for dark energy. It shows the dark energy at work, actively fighting against gravity's pull and winning, smoothing out the cosmic landscape over billions of years. That faint temperature shift is the ghostly echo of the universe's accelerating expansion, written directly onto its oldest light, a permanent record of the moment dark energy began to dominate the cosmos and shape its ultimate fate. The ultimate whisper of creation is still waiting to be heard. The quest for the primordial B-mode polarization, that faint swirling pattern from the universe's first instant, continues to drive cosmology forward. While the initial excitement of a possible detection was tempered by the confounding veil of galactic dust, the hunt has only intensified, leading to a new generation of observatories designed with one singular, monumental goal. These are not mere upgrades, they are technological leaps into the unknown. Projects like the Simons Observatory and the even more ambitious CMB-S4 are being constructed in the world's driest, highest deserts, places like the Atacama Plateau in Chile and the South Pole. Their mission is to achieve a sensitivity orders of magnitude beyond anything that has come before, to finally separate the faint cosmic signal from the loud foreground noise with absolute certainty. The heart of this effort lies in breathtaking engineering. They will deploy tens of thousands of ultra-sensitive detectors called bolometers, which are cooled to a fraction of a degree above absolute zero. At these temperatures, they can sense the minuscule amount of heat deposited by a single photon of the ancient microwave light. These detectors are arranged in massive focal planes, housed within complex cryogenic systems that are marvels of precision, allowing them to scan the sky with a resolution and clarity that was pure fantasy just a decade ago. Success would be a transformative moment for science. Detecting this primordial swirl would do more than just confirm cosmic inflation. It would tell us the energy scale at which it occurred. It would reveal the specific physics of the inflationary field, answering whether it was a simple, single process or a complex dance of multiple forces. This single observation would open a direct window into the grand unified theories that operate at energies 1 trillion times beyond the reach of any particle collider. The hunt for B-modes is the next great frontier, a patient, meticulous search for a whisper that holds the story of our cosmic origins, a story that could redefine our place in the grand scheme of everything. The search for these hidden correlations pushes us beyond the standard map of hot and cold spots and into a deeper mathematical realm. To truly understand the universe's first moments, cosmologists must analyze not just the individual temperature fluctuations, but the subtle, intricate relationships between them. This requires examining higher-order statistics, a sophisticated way of looking for interconnected patterns that link 3, 4, or even more points on the cosmic canvas. The most fundamental of these are known as the bispectrum and the trispectrum. Think of the standard power spectrum as a simple volume knob, telling you how much power exists at different scales in the CMB. It is a 2-point statistic. The bispectrum, a 3-point statistic, is more like a measure of harmony, revealing if specific sets of 3 points have a special, coordinated relationship. It is sensitive to the faintest whispers of non-Gaussianity, the subtle fingerprints left by complex interactions during inflation. The trispectrum, a 4-point correlation, probes even further, looking for the signatures of truly nonlinear, chaotic dynamics in the primordial universe. While our most precise maps have not yielded a definitive, smoking gun signal in these higher-order statistics, they have revealed persistent, subtle anomalies. The data is not perfectly random in the way our simplest models predict. There are hints of unexpected correlations, faint suggestions that the hot and cold spots might be linked in ways we do not yet comprehend. These statistical ghosts keep theoretical physicists awake at night, fueling a myriad of exotic explanations. Could these anomalies be the echo of multiple inflationary fields interacting in a cosmic symphony? Might they point to the presence of exotic particles or hidden dimensions that subtly warped the fabric of spacetime as it was being stretched? Each slight deviation from perfect randomness is a clue, a potential thread leading back to the nonlinear heart of creation. This deeper layer of information suggests that the cosmic microwave background is not a static picture, but a dynamic text, with its most profound story written not in the individual letters, but in the complex grammar connecting them all. This faint afterglow is our universe's oldest surviving photograph, a baby picture taken when the cosmos was a mere 380,000 years old. In that single, frozen moment, we can read the story of everything. It captures the precise instant the chaotic fireball of the Big Bang cooled enough for the first atoms to form, a process called recombination. For the first time, light could travel freely across space, and that liberated light is what we detect today as the cosmic microwave background. This snapshot is not just a relic, it is the ultimate cosmic birth certificate. By measuring the subtle variations in its temperature, we can calculate the universe's exact age, an astonishing 13.8 billion years. We can inventory its contents, confirming that ordinary matter, the stuff of stars and planets, makes up less than 5% of the cosmos, while dark matter and dark energy comprise the rest. This image confirmed the universe's geometry is flat, dictating its ultimate fate of eternal expansion. Every galaxy, every star, every structure we see today grew from the seeds of those tiny temperature fluctuations, the slight overdensities and underdensities imprinted on this ancient canvas. The CMB provides the initial conditions for the entire cosmic simulation, the starting point from which gravity sculpted the vast web of clusters and voids we observe. It is the foundational data set for modern cosmology, the unshakable pillar upon which our understanding of the universe's past, present, and future is built. This single, ghostly image is a time machine of unparalleled power, a direct look back to the cosmic dawn that continues to reveal new secrets with every passing year. The faint hiss that fills our cosmic maps began not as a sought-after signal, but as an unexplained annoyance. At Bell Labs in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were calibrating a massive, ultra-sensitive horn antenna designed for satellite communication. Their goal was to eliminate all background noise, but they were plagued by a persistent, uniform static that seemed to come from every direction in the sky. It was a nuisance, a ghost in their machine that would not go away. They meticulously checked every possible source of interference. They pointed the antenna at New York City, thinking it might be urban radio noise. They investigated radar reflections from high-altitude balloons and even suspected a pair of pigeons nesting in the antenna. They carefully cleaned out the droppings and evicted the birds, but the faint, relentless hiss remained. It was an absolute mystery, a signal with no identifiable source, and it was constant day and night throughout the entire year. Their frustration was the birth cry of modern cosmology. Unbeknownst to them, a team of physicists at Princeton University, led by Robert Dick, was actively searching for this very signal. They had theorized that if the universe began in a hot, dense state, it should have left behind a cool, remnant glow bathing all of space. Penzias and Wilson, hearing of this work, finally understood the profound nature of their pesky noise. That static was not a technical flaw. It was the faint, cooled echo of the universe's fiery birth, the cosmic microwave background radiation. Their accidental discovery provided the first direct, observational evidence for the Big Bang theory. decisively shifting cosmology away from the steady-state model and into a new era. For this serendipitous breakthrough, they were awarded the Nobel Prize in Physics in 1978. This story is a powerful reminder that the universe's greatest secrets are not always found by those who are looking for them, but by those who are simply paying close attention to the unexplained whispers in the static. That single moment of curiosity opened a window to the dawn of time, a window through which we are still peering, uncovering the 25 unbelievable discoveries hiding within that ancient light. That faint hiss, once an unexplained annoyance, has become the most detailed cosmic ledger we possess. From the unsettling alignment of the axis of evil to the profound chill of the cold spot, from the ghostly tug of dark flow to the relentless push of dark energy, these 25 discoveries have fundamentally rewritten our cosmic story. We have seen how this ancient light constrains the laws of fundamental physics, weighs the lightest particles, and serves as the ultimate test for gravity itself. It has answered profound questions about the universe's age, shape, and composition, yet every answer has ripped open a new and deeper mystery. The CMB has not been a final chapter, but a gateway. It points us toward the chaotic dawn of inflation, the enigmatic nature of dark energy, and the staggering possibility that our universe is just one island in an infinite multiverse. This journey through the static reveals a cosmos far stranger, more dynamic, and more wonderful than we ever dared to imagine. If these whispers from the dawn of time have expanded your view of reality, we would love to hear which discovery reshaped your perspective the most. Share your favorite cosmic secret in the comments below, and subscribe to continue exploring the profound mysteries of the universe.